I modified the title a little bit. It's ideas for a design of new synchronization scheme. We had a rush of motivation at the end of last year, early this year, and then we ran out of time and money. So this is what we have right now. Full disclaimer: there's no implementation. It's all in our heads and in the wiki in the working group. So eventually we'll get to an implementation, I hope. But we started that at the end of ECP. And if you've heard anything about ECP, it was a big success. But once it finished, lots of people had to shuffle around and change jobs and focus on other things. So I had to drop some of my MPI engagement because I'm now working more on the application side. And Thomas Gillis, that I've worked with mostly on this, moved from Argonne National Labs to Greener Pastures. So he is doing other things now. But I think it's a good, for me, it was again a good thing to just remember what we actually did and to keep it alive in a way. Many people have heard of MPI RMA as something in chapter 12 that you never get to read when you look at the standard. It actually has a long history, right? So 9 years after MPI 1, MPI RMA was added to the standard. That was 21 years ago, so quite a while. We started with FENS, PSCW, and locks. So all the three things that we have right now in the standard for synchronization were already there. And then we just added small things like lock all and 3.0. There was a flush, so you don't have to synchronize. You just locally finish the puts and gets that you're doing, and then a little more advanced window allocation. And then there was 10 years of nothing, and we started working again a little bit on the RMA chapter, and added more flexible shared memory, for example, and a control on how to deal with atomic operations. That was in 4.1. Just so we're on the same page. We usually talk about origin and target in RMA. So the process that initiates an operation is the origin. The target is where the data goes. Origin can be the same as the target. In this case, we have the target on the left, the origin on the right. There's synchronization primitives like the FENS that synchronizes two processes or more. And then there's completion at the origin. We also call that local completion, and completion at the target, sometimes referred to as remote completion. And the FENS actually starts two epochs, an access and an exposure epoch. Access epoch means that you start accessing someone else's memory. Exposure epoch means that you are allowing someone else to access your memory. So those are the terms we use. The motivation for this work was that we have three synchronization mechanisms in RMA: PSCW, FENS, and passive targets, or locks. And they're not interoperable. You have to finish using one before you can start using another one if you want so. And there are kind of confusing rules around all of them. It's not always, to me, I pity users who try to understand what to actually use in their application. And once you start using one, it's really hard to change to another one. We also, I think there's a realization that RMA is nice because it allows you to move data fast, and we have all the support in the networks for remote memory access. But we haven't solved the problem of synchronization. Synchronization is the hard part, and this is why send receive is great, because you couple data movement with synchronization. When the receive is complete, you know that the data is there. When the send is complete, you know that you can reuse your memory. So that is something that is lacking in RMA. And the other thing that I think really hampers us is that all the synchronization that we have is process scope synchronization, right? So a flush flushes everything in the whole process. A fence is a collective operation, applies to the whole process. And the same in PSCW. So we cannot really have thread local synchronization or thread granularity synchronization where threads can do different things in RMA and then synchronize only their part. So that's a problem. So we set out and thought, what would a clean slate approach look like? If we could start all over again, we've learned, the community as a whole has learned a lot from OpenSHMEM, for example. There was GASPI, so there were different RMA approaches that all kind of took similar but separate routes. And how can we bring all of this together? And so first, a quick review. What the three things that we have right now are fence, PSCW, and locks. The fence is a collective synchronization. So think of it as a flush. You finish all your local operations and then you enter a barrier. The origin of an operation will know that at the end of the fence, the buffers can be reused so that the operations are complete locally. And it will also know that any operations that targeted it will have completed. So you can look at the data that someone else put into your memory. And I hear those who were around 30 years ago that there was actually a machine from IBM that was really fast to do a fence. It was all done in hardware. There was ordering between the barrier and the flush. So under certain circumstances, if you stayed in like a cabinet or something, it's really weird, but it was super efficient apparently. So that's why we have this. But it requires the whole communicator, right? The whole world to synchronize. Then we have post-start complete wait, or PSCW, which is much more fine-grained, and you can actually say, well, I'm gonna start an exposure to this table, and I'm gonna communicate to this table, and all the rest of you have nothing to do with my memory. So I can be very selective on who can access my memory and whose memory I access, right? But it's complicated. So now we have to start creating groups. Group construction in MPI is not trivial, and it doesn't scale really well, right? Because now we don't actually have a communicator that we can work with because we only using subsets of communicators. So it's not really. It can be useful, and we'll see that in a second. But it's complicated. There's a lot to work with here. And again, we only have one signal that we can utilize here, right? So on the process scope, we only have one synchronization mechanism that we can use on a window. And then there's passive target synchronization, which is my favorite, and I would recommend everyone to use that if you ever choose to use RMA. It's basically, I can lock a window, and that means I have exclusive access to that, or to that peer at that place. And then I do my operations and I unlock it, which gives you kind of like a mutex synchronization. And that is that can be implemented quite efficiently, actually. And then there's a separate but equal, no, it's not right. There's a different mode of using one a passive target synchronization where you just say, well, I want to access everyone, all of the windows, and I'm just going to flush my operation. So when you flush, you're waiting for all the operations to complete. But that doesn't give you the synchronization anymore. It's very efficient because you're not, you issue all your puts and gets, and then you wait for them to complete. but you don't get the synchronization aspect anymore. And so applications will start rolling their own synchronization mechanisms, which is not really great either. So the RMA working group set out to say, well, let's simplify RMA and start, how can we be more, how can we reduce the complexity, and how can we redesign based on what we have already. And the first thing that we thought was, well, how about we deprecate PCW, because no one's really using it, right? We didn't know anyone who uses it, and everyone was like, well, this is so complicated. Why would we want this? And then someone came and said, I'm using PCW and it works great for me. And everyone was sad. So we kind of failed at that. Can we take out things and just reduce the complexity of the RMA chapter, going from three synchronization mechanisms to two. So we were kind of bummed out by that, and we didn't really want to take away something that is actually used in practice. And it's kind of the story in MPI in general, right? Every time we think, oh, there's a feature that, like in chapter 13 that no one's ever using, someone will raise their hand and say, well, I know someone who knows someone who has used that in the 90s or something, right? So it's really hard to remove things from the MPI standard. And the question then was, well, why do people actually use PCW? And the answer is that it gives you very flexible bidirectional synchronization, right? You can control when someone starts accessing your memory, or when a different process can start accessing your memory, which means that you can safely read your local data and then say, well, now someone can access it. That gives you some safety guarantees, and the same is true when you're done with your operations on a different process memory. You can say, I'm done now, and the other side can wait for you to say, I'm done now. So this two-way synchronization is really valuable, and it's kind of akin to a send-receive in the end, except that it operates on groups. So it's not a point-to-point, but almost like a multicast or something. But as I said, PCW has process scope. So working with threads is really complicated because you need to join all the threads and wait for threads to complete their operations, and then only one thread can say, well, I'm complete now, and then start the exposure epoch again. So it's not really suitable for what people are doing with like MPI plus X today. So we thought, how about we find one synchronization model to rule them all, right? There's justification for all different ways to synchronize in RMA, but they're incompatible with each other. So can we find something that combines them in one interface? And this is not really new, right? People have been like, this is just a way to think about synchronization signals. A signal is basically a way to say that you're done with something. So you acquire a signal, which means you want to start working on memory, and then you release the signal, means you're done with your operations. So the acquisition waits for prior operations to complete, and the release allows subsequent operations to start. Basically, PCW is that, right? PCW is one signal for all peers. So we didn't realize that this is actually a nice property of that synchronization scheme. So how can we go from having one signal to having many signals in a way, right? So how can we better support thread thread concurrency in processes, and accelerators is a big topic too, of course. We can name signals just through IDs. We can say, well, I'm gonna use signal 1, and another thread or another process is going to use signal 2, and then I can wait for signal 1, I can wait for signal 2. So we have a global naming space through IDs. That's the first thing. And you have to specify how many signals there will be, because we have to allocate some special type of memory for it to be efficient in the network. So this will become part of your window in the end. And then we thought, well, once we do that, we need to have this scheme. The way networks trigger signals often is by hooking, or the way you can implement it is by hooking the signal into another operation. So you can say, I'm going to do a put with an increment somewhere. This is actually what OpenSHMEM does, right? It's one operation on the network, very efficient, nice. But how can we combine the data movement with the release of the signal? Because that's eventually what we need. And in a model like we have it in the MPI today, those two things are kind of separate. Like you can put, and then eventually say, I'm done now. So there's no state that moves from the operations to the signal release. And so we thought, can we aggregate operations, or can we have an efficient way of aggregating operations and telling MPI that here's a set of operations and they should trigger this signal, and then MPI has all the information and can figure out what to do with it. So we started thinking about batches. A batch is a set of operations that synchronizes with the signal. So that you open a batch. I can go. You open a batch, which gets you an object that you can add operations into. And when you close the batch, those operations will be executed. And at the end of the close, you know that those operations are complete. And the nice thing here, the first property, is that now we get thread scope passive target operations, right? So we have an object, each thread can have a batch, and they are all independent. And we can actually manage resources for that batch. And we can aggregate operations and all that nice thing that kind of everyone promised. There's been so many papers about operation aggregation, and no one's really, at least as far as I know, it's not really being used. So we can, of course, now we can couple that with signals, right? The batch open will say, I am going to synchronize with signal B on signal X on process B. So the batch open will have to wait for the signal to become available. So that's your post in PSEW. And basically the batch open is the start. Just giving it different names now. And then you do your operations and you close, which will synchronize with the signal wait, which is the wait in PSEW. And we can make that more complicated. So we can have multiple processes synchronizing on the same signal. Now process A and process C will open a batch that synchronizes with signal X on process B. And they do the operations, close their batches, and the signal wait in the middle there will wait for both A and C to complete the operation. So that kind of gets us back to the groups in PCW, which we may or may not want, but this is kind of the progression that we made in our process. So now we're basically back to a full-blown PCW with what we with this model, with basically groups. Groups that are passed to batch open and signal post. We can model PCW with this approach. And we can use different signals, right? When you create your window, you can say, well, I want to have 16 signals. Then process A could say, well, I'm going to use 2 of them, X and Y, and process B could actually use X and Y with different threads, for example. Each thread will do their own operations and then trigger different signals on process A. So that now we have multi-signal PSCW, multi-threaded. We have thought about the memory semantics because now C++ have actually a memory model, which is nice. That wasn't there when RMA originally was conceived, right? Everything is now in terms of release acquire or acquire release. So really the signal post is a release, the batch open is an acquire, the batch close is a release, and the signal wait is an acquire. All the operations, puts and gets and loads and stores are relaxed. And they synchronize through the acquire and release of the batch and signal operations. The batch close will give you local completion. So once batch close returns, you only know that you can reuse the local buffers. You're not guaranteed that the data is actually in the memory at the target. You will know from the signal wait that the operations that were operating on your memory have completed. And since we only allow these signals, you will still get consistent results. There's no data races, because in order to access someone else's memory, so in this case here, process A and B synchronize with each other in the first case, right, until the very bottom here. I'm not sure I can. Never mind. Here. So this is where A and B have synchronized. B has actually put data into process C's memory. And now if process A wants to read process C's memory, it has to go through a signal. And because these two synchronized and these two synchronized, we know that this is safe here from the synchronization that happens here. So we don't actually need remote completion, which is kind of nice because it allows us to come back before we potentially save a network round trip. And I mentioned fence earlier, which is a collective operation, and we could easily integrate that as well. If you know that kind of have almost a sparse all-to-all maybe, where you're potentially communicating with everyone, we can have a signal that is a fence in the end. So the opening of the signal gives you batch. We combine these two because there's no need to split them again. The signal fence will give you a batch, and it will basically be a barrier in a way. It starts both an access and an exposure epoch. Everyone does their operations. We do keep the batch closed, and then you can wait for the signal to occur. So the batch closed will start a non-blocking barrier in the end, and the signal wait will wait for that non-blocking barrier to complete. That's a way to think about that. As I said, there's no implementation yet. We started Thomas was, when he was at Argonne, he started implementing and experimenting with libfabric on Slingshot 11. And it was, yeah, this is what it was like. It was, I think he was fighting libfabric more than actually making progress on things. So we didn't get very far. We wanted to, but we were hampered by technological problems. So there's, if I could find a student or money to implement this, I would be happy to do that. I think there's some potential here. We also there could be an interesting interplay between persistent batches and device support. So if you describe your operations up front, you just push that batch to the GPU and then trigger it once. That's very efficient, right? We can do that very nicely because we can set up all the network descriptors and then just ring a doorbell on the NIC. And there's also some, this is a bit of a wider discussion, some thoughts about how to restructure atomic operations. We have very general interfaces for atomic operations like MPI. We have MPI RGET accumulate. Jokingly, we could have an MPI RRR get accumulate where we get 3 requests back because you could wait for 3 different aspects of the atomic operation to complete. Whether we want to do that, not sure, but it's the things we talk about in the working group. We have a lot of fun. Dynamic windows are something that is near and dear to my heart because I can actually use that in our distributed runtime system. The problem with dynamic windows today is that you only give a pointer to MPI, and you can send a pointer to someone else and then say, well, here's my memory, you can access that now. But that's not how NICs work, right? It was an interesting idea to do that, but it doesn't work in practice. Very slow because you're not using RDMA anymore. So how can we redesign this to allow for RDMA on a more dynamic window model? So in summary, data movement is easy, synchronization is hard. We don't really give you a good way of doing that today. At least Thomas and I think that signals and batches provide a nice and flexible synchronization mechanism that kind of combines everything we have today into one model, and you can mix and match whatever you need, right? So that's nice. And it gives you, we like to think of it as a separation of concerns. So the window manages the memory, the batches provide the synchronization, and they are 2 different things. So that's potentially interesting. And as I show here, we can subsume the 3 things with one model. If you have any opinions on this, please feel free to contact me. If you're interested in RMA in general, we are meeting sometimes right now. We're picking up again. There's a GitHub page, and if you're interested, I can add you to the group, and then there will be emails when we meet. And that's all. Thank you.
Thank you very much. Are there any questions? Yeah.
So you might not be able to come up with the details, but what were you guys facing with libfabric? Like, what were the issues with libfabric?
I have to remember. I think it was just not in a stable state, so it was crashing, and there were some features that were working, some features that weren't working. For example, I mentioned the triggered trigger notifications basically. So you say, right, hooking up an increment that didn't work at the time for them at least. And he tried to use the fabric on the GPU, and then there was a lot of communication back and forth with the libfabric people.
Because yeah, the libfabric that runs on the QuakeXC systems is quite bespoke compared to just a generic. It's quite bespoke in terms of what it tried. The other stuff that they've stuck into libfabric, besides just libfabric, the open source stuff that you can grab.
Yeah.
Do you think it's just libfabric itself, or the particular implementation that they were running on?
I think at the time it was not. I don't want to say too much.
Okay.
Record.
Okay. We can chat after. I'm curious.
Thank you. Any other questions?
Maybe to add something to this dynamic memory model, I think that's a really interesting topic, especially looking at the models like C++, where you have all these containers which hide stuff. And I see lots of applications having like lists implemented in C++, and having here the possibility to expose them in some way with the MPI model would be really great. Yeah. So, yeah. But I think it's also really hard to make this efficient and really easy to use.
Yeah, we need to find a way to transfer. Basically, we need to transfer the NIC registration key to another process without actually exposing the R key, because we don't want to expose internal information, but having a way to exchange that in some way.
Yeah, and I think it's also, you have to collaborate then with the allocation mechanisms from C++, or because you want to go to the memory registration in the kernel, or
I wouldn't want to. It's a whole separate discussion that we can have about allocators in MPI. It's on my list somewhere in the middle.
Okay.
Agree. We need to do something about that as well. Yeah.
Any other questions?
Hi, thanks for the talk. Can you maybe stress again, I mean, on the point-to-point, I mean, in OpenSHMEM, we have point-to-point synchronization of signaling, and possibly there are similarities to your point-to-point signaling and so on. In OpenSHMEM, it's like you can basically like wait for any value changing or something like that.
Yep.
And then, yeah, you can signal something, and then you're a bit free of combining them. Possibly this could be a bit maybe difficult for tools and tracing back how who is synchronizing with whom. But can you maybe say again, like the differences or inspiration?
Yeah, I mean, it was inspired by OpenSHMEM. I think, if I remember correctly, in OpenSHMEM, the signal is not, well, they don't have windows, right? There's no, it lives in the address space, and I think it's part of the allocation. Yes. We need a handle, right? We need some handle, because we unlike OpenSHMEM, we don't expose the whole memory space. We shouldn't do that. It's a different model. But yeah, I mean, it's basically it's similar in that you can say once the signal passes a threshold, my wait's complete, basically. I actually have a slide for the presentation later on the panel. We do work on a notification scheme in RMA now. So Intel has put forward a proposal that will address this. Again, kind of similar but different to SHMEM. Yeah.